Now we want to apply the idea of strong acids and bases to titrations. So titrations are a really common experiment where you are trying to find the concentration of some sort of solution. You have a solution and it's going to you have it undergo some sort of known chemistry, and you run the reaction until some sort of noticeable change happens, and that's where you're done, and that allows you to figure out, say, the moles of solute dissolved in the volume, which allows you to determine concentration. And so there's a lot of aspects of acid-base chemistry that really lend themselves to titrations. We're going to talk only about acid-base titrations. It is relevant to note you can do other types of titrations with other types of predictable chemistry, but because acid-base chemistry, we know so much about what the stoichiometry is, how things will react. We can use pH to measure how acids and bases are changing in a solution. And so, we have a lot of metrics that we can use to that lend themselves to why we would use acid-base chemistry in titrations. But we can do these in general as ways to determine what the concentration of an unknown is. It's just really common in acid-base chemistry. So the normal setup for a titration would look like this. You have some sort of flask that contains what's called the analyte. The analyte is the solution to be analyzed. So for example, we could do HNO3, nitric acid. And this is a solution where I want to know the concentration of this. Usually you would probably know the acid. There are cases where you don't know what the acid is necessarily, and you just want to figure out the concentration. You can use that to figure out other aspects of the sample you're dealing with. But you want to know the concentration of this. In this case, it's an acid, and you want to do some sort of reaction. So you would probably react it with a base. And in general, you're going to choose strong acids and strong bases to do this because we know that they react so completely. Everything becomes a stoichiometry problem. We don't need to worry about ice tables. So you can react it with KOH. That is called your titrant, and you could use any base, KOH, NaOH, as long as it's strong. You definitely want to choose something that's a strong base. And so the piece of equipment up there is called a burette. It's like a graduated cylinder. It has marks on it that you can notice. If you look, you can see there are marks for volumes there. But this bottom down here is a little tip that you can use to dispense liquid. And so what you can do is basically measure how much liquid of the titrant you add into the analyte. Basically, you add KOH until you react all of the HNO3. So there is some number of moles of HNO3 in this solution, and you add enough KOH until you react with all of the HNO3 that is in that solution. This point is called the equivalence point. So that word equivalence, it's when the moles of titrant added equals moles of analyte at the start. So if you remember, analyte was the HNO3 that was in our flask. We are adding a volume of this KOH solution, and we add enough until the moles are equal. And basically we can see the stoichiometry is 1 mole of nitric acid for every 1 mole of KOH. The coefficients in the equation are ones out there. And so if you had, when the moles of KOH that you add is exactly equal to the moles of HNO3 that you started with, that would correspond to none of the reactants are there. They're all gone, right? All the reactants react, you only have products. And because these are strong acids, strong bases, everything is a stoichiometry problem. Fully react, you'll notice it's a single arrow. When you're doing titrations, how do you know when the equivalence point it happens, right? There's no sign, like the HNO3 molecules don't announce that they're all dead. And so you use what's called an indicator. This is some sort of spectator chemical. There'd be a very small amount in your flask, and it's some sort of chemical that changes properties based on the equivalence point being hit. So if you think about this solution starts with only HNO3, right? So you'd have a very acidic solution. You are adding base to it. And you would imagine that basically you could have an indicator molecule that changes colors from being in an acidic solution, a pH less than 7, to a different color when it goes to pH greater than 7 in a basic solution. So that's basically the idea of what an indicator does. It shows it changes in some way, so that way you can see when you have reached the equivalence point. So let's look at an example of analyzing the results of a titration calculation. You started with 50 milliliters of HNO3. The solution changes color when 45.6 milliliters of 0.265 molar KOH is added. What is the concentration of the HNO3 solution? This is the results you would get of a titration experiment, and the type of analysis you would want to do is to determine that concentration.
All right, so we're dealing with a titration. We have 50 milliliters of the HNO3, it's our nitric acid. We're adding in potassium hydroxide, which is a base. We know if we want to react acid, we need base. And the solution is going to change color when 45.6 milliliters of my 0.265 molar KOH is added. I want to know what the concentration of HNO3 is. This is going to be our standard setup for a kind of titration result where we are trying to determine what the concentration of a solution is. So, you know, with our setup, we'd have what's going on here is we have like our flask. And in our flask, we have a solution of HNO3. And then we have our burette up here. And this is the KOH. And so what we're doing is we're going to add in, we start with the HNO3, and we don't know what the concentration is, but importantly, we do know what the volume is. We got 50 milliliters of that. We just start with some amount of KOH, right? We have some volume, and we know that it's 0.265 molar. And so what we do is we have this reaction, and basically we have some HNO3 and we add KOH. And we know, because it's an acid-base reaction, we know exactly what the stoichiometry is. We know what the reactants are going to be, how they will react, and what product they will make. And so we start with an acid, and then slowly but surely we add in base, and they react together. And basically, when we're going to hit the equivalence point, that would correspond to all of the acid has reacted with all of the base. And so if we think about starting this solution, it is acidic because the pH is going to be lower than 7. And when we hit the equivalence point, what will change is the solution will no longer be acidic, it'll be basic. And so you can put a small amount of some molecule that, say, turns red when the solution becomes basic, right? Once it stops being acidic, say under acidic conditions, the molecule is colorless. And then under basic conditions, the molecule is red. It's an equilibrium system. It's basically just Le Chatelier's principle driving the color. And so it changes color under basic conditions, and we got to get that set up. And so the question is, what volume of KOH did you add, where that would happen? And it's 45.6. So basically from this, we want to know the concentration of HNO3. So these three pieces of data are the standard results of doing a titration to determine that concentration. And so if you want the concentration, we want the molarity of, say, HNO3. That's going to be equal to moles of HNO3 divided by the liters of the HNO3 solution. And we don't know the liters, but we can get that, right? The 50 milliliters, we have that. So the question is, how many moles were there? And so that's the whole point of hitting the equivalence point, because the whole purpose of hitting the equivalence point is however many starting moles of HNO3 you had, you add exactly that many moles of KOH. So we know at equivalence, which is where that solution changed color, we have and we've added that many milliliters of the KOH. We know that the moles of HNO3 is equal to the moles of KOH. And the reason why they're just equal is it's a 1 and a 1 in front of those reactions. So this is stoichiometry, that for every 1 mole of HNO3, you would need to add exactly 1 mole of KOH. So however many moles you started with, that's how many moles of KOH you need to add. So that's at the equivalence point. And so basically the question is, so this, if we got moles of HNO3, we could put that in there. So the question is, how can we get moles of KOH? Well, moles of KOH can come from this molarity. We have a molarity and we have a volume. So the molarity of KOH is going to be equal to the moles of KOH divided by the liters of KOH aqueous. And we have these two values. So we have molarity of KOH and we have liters of KOH. So the question is then just solving for the moles of KOH and plugging that one into there. And so this would be kind of our standard process. We always, based on the molarity and the volume added of what's in your burette, your titrant is the name of that solution. You can figure out how many moles you added based on the equivalence points 1-1. For acid-base chemistry, they're always going to be equal to each other because we're always doing them 1-to-1. We always do one hydrogen transfer at a time, so it's always going to be 1-to-1. But you could have, there are other types of titrations that aren't acid-based that may be like a 2-to-1 stoichiometry. It just comes from whatever the coefficients are up here. But then you kind of just trace all this out. So we'll start with so we kind of start here. And so I have a 45.6 milliliters of my KOH. And I know just metric, I need to get that into liters. So 1,000 milliliters is 1 liter. So that's 0.0456 liters of KOH aqueous. And so then I can plug that into my molarity equation. So 0.265 molarity for my KOH. And so that's going to be my moles of KOH divided by 0.0456 liters of KOH, which tells me that the moles of KOH is going to be equal to 0.265 molarity times 0.0456 liters, which is equal to 0.0121 moles KOH. Just draw a line there. So basically, I'm just taking that volume, turning it into liters, which I need to use for my molarity expression, and then the molarity equation I'm just using to figure out how many moles would be in that volume given the concentration. So we can take that now based on our equivalence. We think that the moles of HNO3 that was initially in the flask is going to be equal to the moles of KOH that we just added. So that would be just the exact same number, 0.0121 moles of HNO3 in there. And so then I can take it and that the molarity of the HNO3 is going to be equal to my moles of HNO3 divided by liters of HNO3, which is equal to, I can plug all this stuff in. I have the 0.012 moles of HNO3 divided by, it was 50 milliliters, so 0.050 liters, telling me that the molarity of my solution was 0.242 molar. And that's HNO3. So titrations are really useful because this HNO3, you don't necessarily know what the concentration of it is, right? You have an unknown solution of HNO3, and you can figure it out based on just the fact that you know the concentration of another solution, and you also know their reaction. You have to know the reaction. That's why acid-base titrations are so common, because we can predict their chemistry with so much ease, that because we have these small, kind of simple, very predictable changes that are also one of the other things that's important to note. This color change you want to see, because you want to get that 45.6, right? You're slowly adding in your KOH. You want to see it happen right away. One of the things that's really nice about acid-base chemistry is, again, the kinetics are so fast. And so the barriers are really low. You just hit equilibrium. In this case, that's all the way to product. And so, these reactions happen really, really fast. And so you're seeing that color change. So you can get a really precise measurement. If it was a slow reaction, it'd be hard to be like 45 point how many milliliters, which impacts the number of digits you get for your resulting concentration. So that's one of the things we want to get really, really precise numbers. Titrations are actually commonly used for what's called standardization, where you prepare a solution, but you don't know what the concentration is. Or you kind of very crudely get into a concentration, like you tried to get 0.25, but you were kind of loosey-goosey with your mass measurements. And so you use a titration to get more sig figs on the concentration. That's a very common use for titrations because you can get really precise measurements when you're working with volumes. But otherwise, it's generally going to be this approach. This is kind of the step 1 is figuring out moles of what's in your burette. Step 2 is relating that to what's in the flask. And then step 3 is actually computing the flask concentration of what was in the flask.
So whenever we're dealing with titrations, again, it's not only acid-base chemistry, but what we would want to know is we have to have a known equation. We have to have a known chemical reaction that we're doing. We want that reaction to be rapid. So basically, we don't want to worry about kinetics. We don't want to worry about it's going to take a long time for the products to react. We also want it to be a complete reaction, go all the way to products. We want it to be something that is stoichiometry based, not ice table for the calculation. We also want a clear-cut change in a measurable property at the equivalence point. Okay, and so all of those properties are why we do so many acid-base titrations, because acids and bases, we can predict our reactions perfectly. Remember, transferring H pluses is a very fast elementary step. We use strong acids to make it complete. So that is one of the things that if you do like a weak acid, weak base titration, that'd be a nightmare. You would definitely want to be using a strong acid, strong bases whenever you can, because the reaction will be complete. You can use stoichiometry. And then there should be a clear-cut change in a measurable property at the equivalence point. That's going to be acidity. We'll see its pH is going to be a pretty big jump at that equivalence point, clear-cut change. And then accurate measurements of the amount of each. That's just kind of a technical aspect of doing titrations. You really need to be careful when you're doing these experiments. Okay. No participation questions in this video. We did not maintain our 1 question per video pace. I didn't think we would. Halfway through the set of videos, maybe there will probably be some more questions on the participation in the back half of the set of videos though. See you in the next one.